Group whiteboard problem 26.3 is asking you to find the electric field at this point, 0.2 meters, 0.1 meters, and 0.3 meters, given this electric potential. V is equal to a negative 2xy squared z plus 4xy volts. Okay, so what we're going to do is we're going to calculate the electric field. And so this is going to equal a negative dV. So we've got the electric field, and this is 3 dimensions. So I'm going to have a negative dV dx in the I hat direction, plus, and let's put the negative out front here like that. So plus dV dy in the j hat direction, and plus dV dz in the k hat direction. Okay, so that's what we want to work with. So let's just split up these derivatives. So dV dx is equal to, so looking at that v, I have a negative 2xy squared z. So I'm going to do d dx of a negative 2xy squared z plus 4xy. And so if I take the derivative with respect to x, the 2 is a constant obviously, but so is the y squared and the z. So for that first term, I'm going to get a negative 2, and I'll pull out all the constants, y squared, z, and then if I take the derivative of just x, I just get 1. So times 1. And then I go to the next term, and 4 and y are both a constant with respect to x, so I'm going to get plus 4y, and then take the derivative of x, and I just get, again, 1. So that's my dV dx. So dV dx then is equal to a negative, let's see, 2y squared z plus 4y. And I'm going to do the same thing now with, well, anyway, before we do that, let's just figure out what that is given the points that they tell us. So they tell us what the electric field is. They tell us to find the electric field at a point. So let's actually calculate what dV dx is. So this is going to equal negative 2. I'm going to plug in y squared. So y squared here is 0.1. So 0.1 squared times z, which is 0.3, plus 4 times y, which is 0.1 meters. And when I calculate that, I get dV dx is equal to 0.394 volts per meter. So that's going to that's what's going to go in right here into this first term. Let's do the next term. So I need the, yeah, okay, so I need 2, okay, so let me make this smaller so I can see it. So dV dy is going to equal d dy of a negative 2xy squared z plus 4xy. So when I take the derivative, so dV dy equals the 2, the x, and the z are constant, so I'm going to have to just pull those out, 2x z. And so the thing I'm taking the derivative of is this y squared. These other things are constant, right? The 2x and the z are constant with respect to y. But y squared, I need to take the derivative, so 2y, plus 4 and x are constant. So I'm just going to have 4x, and then taking the derivative of y, I just get times 1. So let's go up here. So dV dy then is equal to a negative 4xyz plus 4x. And now I can plug that in, so dV dy is equal to negative 4 times 0.2 meters times 0.1 meters times 0.3 meters, and then plus 4 times 0.2 meters. Okay, when I plug that into my calculator, I get that dV dy is equal to 0.752 volts per meter. And now the last one, so dV dz is equal to ddz of a negative 2x y squared z plus 4xy. And when I do that, I get dV dz is equal to, so here the 2, the x, and the y squared are all constant, so in the negative, 2x y squared, and now when I take the derivative of z, I just get 1, so I get times 1, and then this doesn't have a z in it at all, so this is equal to 0, plus 0. So I plug in my numbers, and I get dV dz is equal to a negative 2 times 0.2 meters times 0.1 meters squared. And this is 2, so this is my dV dz is going to give me something in terms of volts per meter. I know that. So plugging in, I get dV dz is equal to a negative 0.004 volts per meter. So I'm plugging all that in, and I'm going to get E is equal to a negative 0.394 volts per meter in the I hat direction. So I know when I calculated this, I got a positive value for dV dx, but I know there's a negative out in front. If I look right over here, I see the negative out in front. So for each of these numbers that I calculate, I need to multiply by a negative. So I'm going to multiply by a negative here. I'm going to multiply by a negative down here, right over here, and I'm going to multiply by a negative for the z term right here. So for this term. Okay, so I'm going to have minus 0.752 volts per meter in the j hat direction, and then plus 0.04 over there, 0.04 volts per meter in the k hat direction. And so I think that's all the question asks us to do, is just find the electric field at that location in space. And so by taking the derivatives, right, making sure we take a negative of each one, we get the vector that represents the electric field at that location.